In Chapter 3, we will discuss transcendental functions. The first transcendental function we will look at is the exponential functions. The exponential function f with base a is defined like this. That is to say, we have our normal f of x notation, and then a is the base of an exponent. And then notice, what is in our exponent? It is the variable. So the big thing to notice about exponential functions is that the variable is in the exponent. But of course, we are going to have some restrictions on what our base a can be. Of course, we're going to say it could be any number. There's not going to be any variables down there, so it is a constant. But we are going to have the restriction that it is positive. That's to say it is greater than 0. And we're also going to have the requirement that it cannot be equal to 1. So a is not equal to 1. And if you think about that for a moment, it makes sense. If we let negative numbers be the base, we would have like -1 squared and -1 cubed. So whenever it was positive, or whenever it was even, it would be positive. But then whenever it was odd, it would be negative. And it just wouldn't give us very consistent behavior. And then if we did let our base be 1, well, then you would have 1 to the x. And well, 1 to anything is just going to be 1 because you're just going to be repeating the multiplication. And this is a constant function, and we've already understood quite a bit about those. Those are a type of linear functions. And those are very different from the exponential functions we're going to deal with. So let's take a few moments and just figure out how to evaluate these. Of course, it's going to all be based off of the certain powers of 3 or 10 or e, and we'll discuss all of these as we go along. So you may need to use a calculator to compute some of these. And it's also very important that you just know how to work with exponents. So let's look at this first one. In this first one, we're letting x equal to 4. And we have a base of 3. So if we substitute in the 4, we have 3 to the 4 minus 2. And again, that minus 2 is going to be causing some transformations, which we'll look at soon. But we'll simplify in the exponent to get 3 squared, which is just 9. So in this case, f of 4 is equal to 9. And now in this example example B, we have g of x equals to -2 times 10 to the x. Notice that this x is just on the 10. This -2 is causing a reflection and a stretch, but for now let's just focus on the computation. So when we plug in -2 for x, we're going to get -2 times 10 to the -2. Now, according to our order of operations, we're going to deal with the exponent first. So that is to say, we're going to just leave the -2 alone. We have to remember, what does a negative exponent do? Well, it'll take anything in the numerator and move it down to the denominator. So this gives us just 10 squared. And then we can just simplify this a little bit further. Because we're multiplying, we just multiply across the top, which gives us a -2. And over the across the bottom, or across the denominators, which gives us 100. And here we have just -10 over 100, or you could simplify that down to -1/50. Now here we have an example of an exponential function with base e. This e is approximately equal to 2.7. Of course, like pi, it is an irrational number. That is to say, it just continues on forever with decimals. But for all intents and purposes, we can think of it as about 2.7. We use the letter e to symbolize this number because the properties of it were developed by Leonhard Euler. So, of course, looks like Euler, but is pronounced Euler, and hence his name starts with an e, and we've notated this number, or this value, with the appropriate letter. So if we just plugged in x equals 1 for this function, we would get e to the 1, which, as I mentioned, is going to be approximately 2.7. In this last example, j of x, we're letting x equal to 0. So we have 768 as our base. We raise it to the 0 power. And of course, anything to the 0 power is just going to be equal to 1. So right here, what we've obtained is a y-intercept for the graph of the function, and we'll look at that in the next page.